Next, we're going to learn about a concept called the Lagrangian derivative, the derivative that flows with a flow as opposed to an Eulerian derivative, the derivative that's fixed with respect to space. And we're going to learn how the two are related. The Lagrangian derivative is often denoted by capital D, d by dt. And the Lagrangian derivative is defined as the sum of the Eulerian derivative, d by dt, plus the advective term, u dot grad, like so. We've written this in an operator form. We might think of it as operating on something, but we can think of this Lagrangian derivative as being defined sort of on its own in this kind of form. This first part of the Lagrangian derivative, this is the familiar Eulerian derivative right here. So this is how something changes locally, local changes at a position in space. And then this bit here is the advective part, advection. This is how something changes non-locally when it's carried by flow. Carried by flow. It takes the form of u, some velocity u, dotted with the gradient dot grad, u dot grad. So this operator as a whole, it's effectively a scalar operator. It can operate either on scalar quantities or vector quantities. And that is because we take our vector u and our vector derivative and we've contracted them together, which reduces their order. All right. Before we get into a little more on the Lagrangian derivative, let's remind ourselves of some of the ways of writing these, because we're going to look at some of the terms. In a Cartesian geometry, and Cartesian, that just means a sort of flat geometry, Cartesian geometry. So one that includes things like x and y and z. In a Cartesian geometry, we might write our velocity as a bit pointing in the x direction and a component a bit pointing in the y direction and a bit pointing in the z direction. One of the conventions that we'll use a lot and that you'll see quite a bit is to call the x part of the velocity u and the y part here v and the w part z. So these are scalar components of the vector u. They get their vectorness from these hatted unit vectors, x hat, y hat, and z hat, right? This x hat represents pointing in the x direction, pointing in the y direction, pointing in the z direction, and then w is how much z, v is how much y, u is how much x. It's confusing that the component in the x direction is also the vector symbol itself, but changing the vector symbol here to something else doesn't really help either. Sometimes people use v hat or v vector, but then you've got a v and y. So it's one way or the other. It's going to be a little confusing. One other way that we'll sometimes write it, an equivalent way of writing it, but just a different notation, we'll sometimes write it as u is equal to u in the x direction. So this is like the x component of u pointing in x hat plus u in the subscript y direction in the y hat plus u in the z direction in the z hat. And this is a little clunkier because it has some subscripts, but this has the niceness that it generalizes to other geometries. So like for a sphere, we might have ur, u theta, and u phi pointing in the r hat, theta hat, and phi hat directions. And that's better than using just random letters in a sphere. But in Cartesian, sometimes we'll use subscripts, and sometimes we'll use u, v, and w. And you'll see that convention throughout the literature and throughout our textbooks. With these on hand, I want to now think about the advective operator. So we have this advection. And the advection operator, right? This is this u dot grad operator, a contraction of u with the gradient operator. And I want to think right now just in Cartesian, just so we can get a little picture of this. So u dot grad, what this really looks like is u d by d in the x direction plus v d by dy and plus w d by dz. Or equivalently, u in the x direction, d by dx, plus u in the y direction, d by dy. Get my y cleaned up there. And u in the z direction, d by dz. Before contraction, this is a vector, and gradient is a vector, and they both have a sense of direction. But after contraction, this is just a scalar, right? It's now saying that the amount of change in the x direction is going to be multiplied by the velocity in the x direction. The amount of change in the y direction is going to be multiplied by the amount of change in the y direction, and the change in the z direction is going to be multiplied by the velocity in the z direction. So an interesting thing about this advection operator is that it depends not only on the velocity, but also on the gradient. Something can only be pushed by a flow if there are gradients to the thing. If I have some blob like this, and I have some velocity this way, u vector, then that velocity will take this blob and it'll move it over here, and then it'll move it over here, and then it'll move it over here. Zoop, and I'll move it along. But if I don't have any gradients, if I just have something that's everywhere all the same, so if I have like some box and I have it like all full of my dye here, my ink, and then I add some velocity u to it, well, there's not actually u dot grad ink, I'll call it maybe q for my ink. Here it would be 0 because there's no grad q, and here u dot grad q is not 0 because there's both a velocity and a gradient. So blobby things with edges and gradients, those can be pushed and moved by a fluid. But if everything's the same everywhere, then if the fluid's flowing this way and you're standing, here in the middle of this, you don't actually see any more ink go past you because you're in the ink and more ink comes by you. Up here, if you're standing here and the fluid's blowing, then the fluid blows, and like sometimes you're not in ink, then the ink comes over you and then the ink goes past. So the advective term and how it changes things depends on both velocity and gradients. All right, so now we're going to think a little bit about this Lagrangian derivative and what it lets us do in writing our equations. The Lagrangian derivative can be really helpful in thinking about how things change, and also in just compactly writing our equations. So if we take our momentum equation here, d by dt of u plus u dot gradient of u, put our vector symbols on things here, clean up our dot product, clean up our t, which lost its little hat. This is equal to minus grad p over rho. If we wanted to put this in Lagrangian derivative form, I've written it in a convenient way where we have our left-hand side in a Lagrangian derivative form and our right-hand side as the forces. So this is d u vector by d t equals minus a gradient of pressure divided by density. So this gives us a nice compact form that we can write our momentum equation in. This is our nonlinear Eulerian momentum equation. This is nonlinear Euler. And the nonlinearity lies both in the grad p over rho, if we're compressible, but also it's hidden inside this Lagrangian derivative. And that's because this part here is inside the derivative, and this part is a quadratic nonlinearity of our system.